Grab a chair. All right, Rob, we'll get started in like a minute, okay?
Sure.
We're just setting up around a table right now because projector's not working.
Okay.
There's only like 8 of them now, so.
Okay. Sounds good.
All right, come on, guys. Get started. So, make sure you can see. Okay, it's not the perfect situation, but I thought my adapter would work, and it's not. Jason, grab a chair. Slide up, right up here. He's already kind of walked me through this. So I know what's going on. All right, Rob, you can get started.
Okay. Okay, can you see my screen?
Yep.
All right, can you see that? PowerPoint? Kevin?
Yep.
You can see the PowerPoint?
You're paused. We just see your head, and it's paused.
Okay. All right, how about now?
Like this?
What do you see from my end?
A pause screen of you.
Really? Let's try this. All right. Do you see my screen?
We see your home screen.
Okay, good.
I meant like your Skype screen.
Yeah, do you see a PowerPoint now?
No, we just see your what is it called? Your your profile picture or your avatar. There we go.
Okay. You good?
Yep.
Okay, hi everyone. Today what we're going to do is talk about how 3D computer-aided design is used in the engineering industry. My name's Rob Lacera, and first I wanted to show you the agenda of what we wanted to talk about today. I'm going to give an introduction about myself, and then we're going to talk about something called engineering deliverables. And subsequent to that, we're going to talk about the history of how engineering documents and drawings were generated. So through history, there were various modes and methods that engineering documents and drawings were created or generated through models, through hand drawings, and then starting in about the early 80s, 2D CAD, 3D CAD, and I'm even going to talk about something called 4D CAD. And then what I'm going to do for you is do a very short model review to show you how we do model reviews with our clients nowadays. And then field any questions that you might have.
That's where I should be.
So, in the way of introductions, my name is Rob Lacera. I live in Haddon Heights, New Jersey. I've worked in the engineering industry for over 35 years for both owner companies and also for what's called EPCM firms, engineering, procurement, and construction management firms. I currently work for Jacobs Engineering in Mount Laurel, New Jersey, as a senior project manager. Jacobs, if you haven't heard of them, is a worldwide EPCM firm consisting of about 60,000 people on a worldwide basis. I have a Bachelor in Science degree in Chemical Engineering and an MBA, both from Drexel, and I'm also a registered professional engineer in 2 states, New Jersey and Pennsylvania. I'm also, kind of in my spare time, if you will, an adjunct professor at Rowan University. I'm currently teaching an online course for Rowan entitled Quality Systems in the or Quality in Engineering Systems. I do have a State of New Jersey teaching certificate of eligibility in math, engineering technology, and chemical technology. And the way that I met Kevin, or Mr. Knaus, excuse me, is through Project Lead the Way. I am on Project Lead the Way advisory board for a number of schools. One of them, of course, is your school, Deptford High School. Also on the board for Camden County Technical Schools and BCIT as well. In what little spare time I do have two granddaughters that I like to spend time with. I enjoy all sports. As a matter of fact, next weekend, I know Kevin will be, Mr. Knaus will be jealous about this. I'm going to Clearwater to see my first Phillies spring training game down in Clearwater, Florida, for a short little vacation. I play golf. I do volunteer sometime a week on a monthly basis at a food kitchen in Camden. I do brew beer. And I'm looking to get a company called STEMBridge off the ground. And if we have a little time, I'll talk a little bit about STEMBridge. And that's one of the reasons I'm here today. Is STEMBridge is really the concept of it is to infuse STEM subject matter experts virtually into the classroom, particularly at the high school level. So Mr. Knaus was nice enough to let me try this pilot, if you will, for STEMBridge. And that's one of the reasons that we're doing this presentation today, in addition to hopefully giving you something to think about relative to the engineering and the STEM curriculum. So that's in the way of introductions. As I said, we're going to talk about something called engineering deliverables. So the EPCM, again, that was engineer, procure, and construction management firms, work for owner companies or clients. So the company I work for, Jacobs Engineering, works for different companies such as DuPont, such as Dow, such as Honeywell. Those companies contract with us for what's called engineering services. So typically EPCM firms are multidiscipline firms that include generally these disciplines that you see here. These are various engineering disciplines. We have folks in our office in Mount Laurel who are subject matter experts in all of these different disciplines. Typical engineering deliverables that we produce for our clients are things like specifications, such as equipment specifications, instrumentation, and electrical equipment. We will specify the equipment that's necessary for an upgrade or a new plant. We developed something called scopes of work, which is basically a written document that would tell contractors what needs to be built and what needs to be done. But our major deliverable is engineering documents and drawings. So generally they're used for constructing new process facilities, buildings, and infrastructure. They contain equipment plot plans, piping plans and sections, isometric drawings, concrete and steel plans and details, and electrical and instrumentation plans and details. And these deliverables are what we're going to be talking about today. These are our major product to our clients. These are drawings and documents which basically show a contractor how they should build a particular upgrade or a new facility for one of our clients. They're known as, at least they used to be known as things like, they're called blueprints. You might have heard that term. It's kind of an older term now. It used to be done on blue paper, light blue paper. It's not done that way anymore, but just to give you an idea, that's what we're talking about. Plans and sections and deliverables for building a new plan and a new system. So how are these engineering documents generated? That's really the subject of our talk today. And way back when, models used to be built. So these are small. This is a tabletop model, to scale. We're showing to-scale representation of process plants to give people a 3D perspective. And these were popular back in the 60s and the 70s. So these are, it's a little hard to see, but these are basically on a tabletop, and it's a to-scale version of a plant system or upgrade. And these were done so that the client could visually see in 3 dimensions what it is that's going to be built. So this is interesting because way back in the 60s and 70s, there was an understanding that the client needed to see something in 3 dimensions to give them a good perspective of what their plant was going to look like. Because as we know, when you have a drawing is 2-dimensional. It's length and width, of course. Whereas with 3 dimensions, you not only have the length and the width, but you get the height perspective, and it gives you that 3rd dimension. So interestingly enough, way back when, while CAD wasn't invented yet, of course, they were thinking about how can we show our client what the proposed design looks like in 3 dimensions. So following that, and up to about maybe sometime in around the mid-1980s, hand drawings were very popular. And you've probably seen these. These are, again, what are called blueprints or drawings, if you will, engineering drawings. And they were done on what's called a drafting table. Looks a lot like I'm circling it with my cursor here. You've seen these, I'm sure. They typically use drafting paper, or they use something called mylar. And again, this was very popular up into the 1980s. So it's basically done by hand, if you will. Hand drawings. As you can imagine, if you made a mistake, you got out the eraser and you had to do it, you had to erase it by hand. Let's say the client looked at it and said, well, gee, I'd like to move this here, or I'd really rather this pump be over there. You had to basically either start over again, or you had to erase it. Think of an old-fashioned typewriter. If a mistake was made, there wasn't like, when we're working with Word today, you don't just go in and just backspace. With a typewriter, you had to either use some correction tape, you had to erase it by hand, or you had to start the document all over again in some cases. Very tedious, very time-consuming. So following that, starting in about the 1980s, that was the advent of 2-dimensional, what I call a CAD, or sometimes the last D is not on here, as you know, but CAD stands generally for computer-aided design and drafting. So 2D design, CAD was developed. The 2 big programs that were used and still are used much of today for the generation of engineering documentation is MicroStation by a company called Bentley, and AutoCAD, which is now owned by a company called Autodesk. And these are the softwares that are generally used in what we call the process industry. It's basically an electronic drawing board, and the main advantages of CAD are that making revisions are much, much simpler. It's now, it's now a keystroke. It's just like typing a Word document. You can get rid of lines and shapes very simply and start over again. You can copy and paste very easily. So if you do make and design a pump system, if you will, when it comes time to make the next pump system, you can copy the one you did before and paste it in and just make some modifications. You don't need to start all over again like you did when you were doing a drawing with a pencil. You had to start all over again, even though maybe that pump system was identical to one you've already drawn. Standardization is another advantage. And when I say work split or work share, a lot of times what we do in our industry is we work with something called a high value center. Jacob's High Value Center is over in Mumbai, India. So via CAD and via electronics like this, what we can do is take a project and we can split it up into different components, and we can send some of it off to India to be designed in India, where it's the labor is cheaper, and what we can do is basically hopefully do our designs for what we call a higher value for our clients. Namely, we can do them cheaper. So that's 2D CAD. And gee, I don't know exactly when, but not that long ago, 3D CAD came into vogue and was brought to bear. So some of the main 3D CAD programs are called PDMS, which stands for Plant Design Management Software. That's by a company called Aviva, and another software called PDS, which is an Intergraph product. And these are generally used in the process industry. And these are what Jacobs uses for plant design and retrofits. These are the softwares that we use at the company that I work for day in and day out to do our CAD work. There's also some other 3D software. Some of them I know that you're familiar with as part of your curriculum at Deptford High School. Revit is a building information model, or what's called a BIM, and that's an Autodesk product. There's another software called Inventor, which is generally used for mechanical or machine design type systems. That's also by Autodesk. And there's a software called SolidWorks, which I'm sure you've heard of. That's for doing solids modeling work, and that's by a company called SolidWorks. So what are some of the main advantages of 3D CAD? So some of the main advantages are all the advantages that I showed you for the 2D CAD. In addition to that, it enables the client to visualize the plan in 3D. So here we are, 2015, and we're enabling our client to visualize the plant before it's built in 3 dimensions, much like they did back in the 60s with a to-scale model. I find that very much like we've come full circle, although now it's done electronically. And what we're going to do at the back end of this presentation is I'm going to show you a very quick model review of a model that I have brought up on the screen here. The model reviews allow you to do what's called walkthroughs, where you basically walk through the plant, almost like a virtual type of look through the plant, so the client can get a good perspective of where valves are located, where equipment's located, how much room do they have for constructability, for maintainability and operability. You don't want the operator to be squeezed in. That's a safety issue. Let's say there was a problem and you didn't leave the operator enough room and they couldn't get out of a certain area if, say, there was a fire or there was a leak in a chemical system. So a lot of this has to do with safety, which is very big in plant design nowadays, to make sure the operators have the required room that they need to do the work that they need to do. There's also something in 3D CAD called clash detection. It's a very comprehensive quality assurance, quality control tool. Essentially what you do is you do your design and you run a routine where you say, I would like you to run me a report and tell me everywhere that structural steel is contacting pipe, because those are the 2 main components you'll have in a model for a chemical plant, steel and pipe. And generally they shouldn't be hitting one another, because you don't want pipe running through a platform. That means you made a mistake. But clash detection will look through the model automatically, and it'll run your report, and it'll tell you every place that pipe and steel are hitting. And then what you do is you go to each one of them in the model and you look. Now, if you mounted some pipe to structural steel, that's an acceptable clash. So you just go past that one. Sometimes what you'll find is you did make a mistake and a piece of pipe runs straight through a platform. So what you have to do is reroute the pipe, or you have to change the platform. Now, why is that important? It's very simple to do on your computer. Reroute a pipe is easy to do. Let's say you missed that. You're out in the field, and this is big pipe, say it's a 12-inch pipe, and they're pipe fitting it out in the field, and all of a sudden it hits a platform. Now here you are, you have all these contractors, you're in a tight schedule, and pipe's hitting steel. Now what are you going to do? You can't just go in your computer and reroute it. You have to start cutting pipe, you have to start cutting steel, and believe me, if you're doing that in the field, it gets very, very expensive. Therefore, you're going to have a client who's not real happy, because you're having additional costs, you're having a schedule issue, so you really don't want any clashes. So this clash detection feature of 3D is really a very, very nice feature and a very big advantage. You can cut orthographics. Orthographics is a fancy way of saying 2D drawings. You can cut orthographic plans and sections right from the model and annotate them into 2D deliverables. So if you do your design in a 3D model, in order to get your drawings or your 2D drawings out of the model, you can cut the orthographics directly from the model and annotate them, and now you have your deliverables to give your contractor. And some sophisticated contractors nowadays don't even require that you cut them to 2D deliverables. If you give them the 3D model, these contractors bring computer hardware out into the field, and they actually build the plant systems right from the 3D model. So that's kind of state of the art nowadays. A lot of contractors are doing that, and we don't even have to cut orthographic drawings from the model. So frequently we do work in the 3D environment, even if the client only requires requires 3D deliverables. Some of our clients don't care about the 3D model. They just want the 2D deliverables. We at Jacobs, though, do the work in 3D anyway. That way we can use some of these advantages like clash detection, and then we cut the 2D deliverables from the model and we give that to the client as their deliverable. I mentioned before something called 4D CAD. 4D, the fourth dimension, if you will, basically incorporates time into the 3D equation. So animation of how a space is transformed over a period of time gives you that fourth dimension. An example would be showing the construction of a new process unit over the time frame of a project schedule. So just think about if you were watching the construction of a new process unit over time, and basically you saw the animation of how it was built. That time, if you will, gives you that fourth dimension. And this is a live link for some articles on 4D CAD. I'm not going to fire that off for the sake of time today, but I will give Mr. Knaus this presentation, and you can look at this in your classroom. It gives you some articles on exactly what 4D CAD is all about. So, as I mentioned before, what I'm going to do is a quick demonstration of a 3D model review to show you what we would do with a client if we designed a model for them, how we would sit them down and walk them through it so that they can look at it and approve it, if you will, before we cut our 2D deliverables. And I'm going to use something today called Navisworks Model Viewer, and it's an Autodesk product called Navisworks. So what I'm going to do is call that up here. I hope you can see the model in your screen, folks.
Yep.
You can see it? Okay.
So, is it possible a little bit bigger?
Oh yeah, a little bigger, yeah, sure.
Like maximize it to the screen?
Yeah, just maximize it. I'm going to zoom in a little bit too.
Okay.
All right, so this is a process system model, 3D model, and again, this is called Navisworks. So first of all, what you generally do with a client is we take them through what's called a fly-through. So what you do is, and I'm not the world's best model driver, so you'll have to forgive me, but basically you just kind of zoom around, if you will, like I'm doing here in 3 dimensions. Try to give them like an ISO view, isometric view of the entire system. What you can see is you see process equipment, you see pipe racks, you see pipe, you see structural steel, and basically this was a process unit that a client wanted to have designed, and what we did is we designed the equipment, the piping systems, and the structural steel to hold it up, and all the instrumentation and electrical systems to go along with it. So you first do a fly-through. I'm going to stop right here. And you kind of walk into the model, if you will, is the next thing that you would do. And I'm going to pan up and down a little bit. And you see we have one of our friends here. He's already in the model. There he is right there. Pan down a little bit. Okay, here we go. Excuse me, sir. Thank you. Okay, and here we are. So here you are. So just let's stop for a minute and think of what we're looking at here. This is something that we designed in Navisworks, or actually we did this in PDS, and this is the process system. So it hasn't been built yet. It's all electronic. There's not even any drawings cut from it yet. And what we're doing is we're sitting the client down in a conference room and we're walking them through this model. And basically, if we were going to do this, after our fly-through, we would actually go line by line and ask the client if they approve of the routing of where these valves are located. This is a hand valve here. Ask them if they approve of the hand locations, how the pump is laid out, and so on and so forth. And this is before anything's built, because imagine if we built this and the client said, well, gee, that's not what I really wanted. Well, as you can imagine, we now have a very large problem on our hands. So we'll walk them through the model like this, and we have some features this is called the look feature. So basically, it's like if you were standing here and you were just looking around, if I'm looking up now, of course, You see, what it looks like if you look up. If you look to the side, you can see your perspectives, what you would see, how much room you have, and so on and so forth. There's some heat exchangers over here. There's a large tower that you see the base of the tower right there. There's, and again, some more pumps and so forth. Another feature that the 3D software has is,
Rob?
let's say, yes.
The students have to check out and go to baseball and sports.
Okay, all right. Well, that was pretty much it. I was going to show you a few more features, but if there's no questions, like I said, I'll email the presentation to Mr. Canals, and I thank you very much for your time.
Yeah, I think they liked it.
Okay.
Hmm.
Can you see me now?
I see myself on your screen.
Let's see. Let me do that. There we go. How's that?
Perfect.
Were you able to see the model review fairly well, or was it a little too small?
No, it was good. We out of it. I think this, like, I saw some heads turn when they saw it when they navigated through the actual plan itself,
Mm-hmm.
and they got to see more of the perspective that that person within the model saw.
Right. Okay. How about the presentation itself? Kind of leading them through how it used to be done, how it's done now, things like that. Is that?
Yeah,
was
it's
that-
good. I wish they just showed up a little bit sooner. I think they kind of dilly-dallied to get here, and we lost
Okay.
those couple minutes.
Okay.
So.
All right, well, good. I mean, I hope I hope there were a few, heads nodding up and down, or a few, it was interesting to them. If you get any feedback, either positive or negative, let me know. I'd be interested to know what they thought.
I like the presentation. I think I had a lot of good value to it. I just want to get their feedback too,
Mm-hmm.
and just see what they thought. I know that when you and thought was pretty cool.
Say that again. You froze up there just for a second. You were saying what was cool?
I think they saw when you took them through the 3D model. I think they
Right.
thought that was the coolest part because they do a lot of work with the software already.
Mm-hmm. Yeah. They're using Revit?
Well, we had sophomores in here, and they still use Inventor. They're using like a lot of Robot C now.
Mm-hmm.
They're doing a lot of programming.
Mm-hmm. Okay. Well, then they would.
Freshmen are using Autodesk, Inventor, and Revit.
Okay. All right. Well, Kevin, thanks very much. I really appreciate you allowing me to do this pilot. I actually taped it on a software that I have here. It's called EVAER. It's called. But I taped this just so I can kind of see what the first STEMBridge pilot looked like one day when we look back.
Yeah.
But I thank you. Thanks for your time and setting this up. I really appreciate it.
Oh, thank you. This is the stuff we're looking for.
Okay.
All right.
Yeah. All right. Well, thanks. I'll be chatting with you soon.
Yeah, if you want to shoot me an email, maybe next week I'll try to get feedback from the students and reply to it.
Okay. And I'm going to send you the presentation as well in case they want to look at it on their own.
Okay, that works.
All right. Thanks. Have a nice weekend.
You too. Thanks, Rob.
See ya.
Bye.